So if we manage to pull something like this off in the future, the solar gravitational lens, the resolution of a telescope that had light magnified by our sun would be 10 to the minus 7 arc seconds on the sky, many, many orders of magnitude more refined than what we can see with any of our current telescopes. We wouldn't have to worry about the transit light source effect anymore because we don't need to worry about the transits. We can study the planet as itself, and we could actually resolve continents or oceans if they existed.
This is CBS Eye on the World. I'm John Batchelor. David Livingston is here, Dr. Space himself, my colleague and co-host and co-pilot. This is Hotel Mars, and we're headed 40 light years out, thanks to Julien de Wit at MIT and Benjamin Rackham at MIT. These two men are astronomers, and they're going to take us to an ultra-cool dwarf, a subset of red dwarfs, which is the most popular star in the solar system. If you're asking, we've got a yellow dwarf. We're very lucky. But we're going to the exoplanets of an ultra-cool dwarf named TRAPPIST-1, as in the religious order, TRAPPIST-1, 40 light years out. Julien, I begin with you because our conversation is wonderful, and you're very generous, you and Benjamin, to come on and talk about the matters that you've been working on for many years. What is an ultra-cool dwarf, Julien? How should we think of it? Why does it have all these planets, 7 so far, around it? Good evening to you.
Hey, good evening. It seems to me that the best way to start thinking about TRAPPIST-1, this ultra-cool dwarf star, is actually not to turn to our own sun, but to turn to Jupiter and its systems of moons, and look at how close they are to Jupiter, and appreciate the fact that something as small as Jupiter has managed to form planet, and then think of increasing a tiny bit the mass of Jupiter, just enough so that it could kickstart fusion and be a star per that classification. And you would basically be looking at a star like TRAPPIST-1. So TRAPPIST-1 is a star. It is 10 times smaller than our own sun, so literally the size of Jupiter. And it has managed to form in its vicinity 7 Earth-sized planets. And so the reason why we care about these is because when you're such a small star, you're much cooler. Our own sun is 6,000 Kelvin or so. This star is about 2,500 Kelvin, which means you can take a planet and bring it much closer to the star and still have it be potentially habitable, meaning the right temperature to harbor liquid water. And the reason why we care about those stars is because they are so small that when you take a terrestrial planet and put it in front of it, it's masking a relatively significant portion of the star, which means it's easier to study planets that are as small as the Earth in front of such small star than it is in front of sun-like star.
Benjamin, the James Webb Space Telescope, what is it? What can it do that we've not had before? I understand it's not visible light. How does it work, Benjamin?
Yeah, the JWST, or James Webb Space Telescope, is the latest NASA flagship mission that was launched a few years ago out to L2, the second Lagrange point. And out there in space, it is our best eye on the universe right now. People might compare it to the Hubble Space Telescope, which has been giving us amazing data for more than 30 years now. But Hubble has basically a diameter of 4 meters, and James Webb Space Telescope has a diameter of 6.5 meters. The collecting area scales with the square of the diameter. So James Webb gives us significantly more collecting area to make more precise measurements, and it operates in the infrared. So the very bluest light that the James Webb Space Telescope can see is about the reddest light that we could see with our eyes, but then it can also see light that's much redder, all the way out to 15 microns, which is about the color of us when we emit in thermal emission. You know, if you had 15 micron eyeballs, you could see Earth and all the things on it glowing, and that's the kind of light that James Webb is able to study much better than anything else we've had before.
David, you have a question for the gentleman.
I understand that with James Webb, you have some sort of contamination with the imaging. So can you explain that, and how do you get around the fact that you might have contamination on what you're viewing or studying?
Yeah, so what we call a stellar spectral contamination or the transit light source effect is a particular signal that we get when we're studying transiting exoplanets. Transiting exoplanets give us this amazing opportunity that Julian talked about because we can detect them more easily than other planets, and we can study their atmospheres more easily than any other planets we know of today. We can talk about that a little bit more in the future, but there's also a challenge with transiting exoplanets, which is that the transit method in practice also encodes information about what the surface of the star looks like. So if the star was a perfectly homogeneous light bulb and you just had a planet passing in front of it, we would be able to measure the size of that planet. We'd be able to measure the atmosphere of that planet really easily. But because stars are actually interesting, chaotic environments with interesting features like spots, these cool magnetic active regions, or faculae, these warm, hot magnetic active regions on the star that are splotchy and all over. When you have a planet that transits in front of it, the transit signal is going to encode both the signature of the exoplanet's atmosphere and the patchiness of the photosphere, the heterogeneity of the stellar photosphere. And that's the signal that we've started to call stellar contamination in shorthand. And it's something we need to get a better handle on to really utilize JWST to study transiting exoplanets.
Julien, TRAPPIST-1, you're not studying the star alone. You're looking at the planets. What is it that you're looking at the planets for? What's the hunt, Julien?
Yeah, well, as you highlighted before, these ultra-cool dwarf stars are the dominant population of stars in the Milky Way, right? And we know they form planets. And so the big question we have right now is, are these planets able to sustain an atmosphere? And if they do, could it be that they're also able to have liquid water at the surface? Because if they do, then the Milky Way is host to a bunch of oases. If they don't, then it may be just a dry desert world flying around. And so where we're at right now is using the technology we have at hand to search for signs of atmosphere, to be able to distinguish between them being bare rock mostly or actually having atmospheres. And if so, what kind of atmosphere? And that's really what we're eager to do.
So the atmosphere is what you're studying.
We're searching, yeah, sorry.
Right. And the atmosphere will tell you what the planet is, will tell you what's on the surface?
Depending on the type of atmosphere we find there, if they have any, then we'll be able to try to dig further and further potentially down to the surface. If they don't have an atmosphere, then there's methodology that we have developed that can be used to tell us what the surface is made of, so what the planet are actually made of. But being able to detect an atmosphere and starting to constrain what the atmosphere is made of is not necessarily directly tell us about what's going on at the surface. There might be ways to do so, but at first, as a first step, it won't be possible if they have an atmosphere to say exactly what the surface is made of.
Benjamin, if somebody was 40 light years out directing an alien James Webb at us and our atmosphere, what would that tell them, Benjamin, about us? Would it give away the fact that we have difficulties at airplanes?
Yeah, so if we reverse the picture and we were the transiting exoplanet and there was an alien astronomer watching us, the first thing that they would know is the size of our planet by the total amount of light that's blocked as it passes in front of the sun. And they would know that, okay, there's this planet that's about on a 365-day orbit. We know it's 365 days because we see one of these transit events every 365 days. And we know that that planet's about 1% the size of its star. So they would know that they're talking about something in the rocky regime. For a planet to be as small as Earth, it has to be predominantly rocky. And then if they had precisions beyond what we can do, they would see that as Earth passes in front of the sun and they measured the amount of light blocked at different wavelengths, there were some wavelengths where there would be about 1 part per million more light blocked than normal. And those are the wavelengths where molecules in our upper atmosphere are absorbing light as well. So Earth's blocking light from the sun, and this annulus of our atmosphere is blocking light as well. They could track down by which color of light is being blocked. They could say, oh, there's definitely water in this atmosphere. There's ozone in the atmosphere. That's interesting. And there's a little bit of carbon dioxide. and methane and some other features. But what would be really interesting would be this disequilibrium between having lots of oxygen and ozone in our atmosphere and still having some other molecules like methane present, carbon dioxide present. That could point them to something interesting like a global biosphere that's happening on Earth.
Can I add something to that, John?
Oh, surely.
Because everything Ben said is 100% right. And I think for the audience, it might be good to highlight the fact that when Ben says if they had a better technology that we do, this statement only relates to the fact that the signal that you capture is directly proportional to the planet to star area ratio. And because our sun is 100 times bigger in terms of area, so 10 times bigger in terms of radius, 100 times bigger in terms of surface, larger than TRAPPIST-1, then the science that we can do now for Earth-like planet in front of a TRAPPIST-1-like star is something that's challenging in front of a star like our own sun, because the signal is 100 times smaller, right? But if we had a star like TRAPPIST-1, not our sun, then all of what Ben described could be done with a James Webb Space Telescope around another civilization. And the thing that they could be looking for is ozone, because ozone will be a terrific marker for something going on in our atmosphere. Because to have so much ozone as we do, you need to be able to pump up quite a bit of oxygen. And that would be a really interesting signal that they could dig further into.
We are 40 light years out from Earth. TRAPPIST-1 is the name of the ultra-cool dwarf, and it is blessed with 7 planets. B and C have had their own paper some years ago, so I'm going to start there. David, you have a question about B and C.
Are they primarily of interest because of their special features, or because this happens to be a system that's relatively close to Earth and our technology allows us to begin exploring it?
Benjamin, you want to take that, and then Julien?
Sure, yeah. So we love all the exoplanets, you know. They're all great in their own ways, and you know, everything from hot Jupiters to temperate Earth-sized planets. But there is sort of a holy grail for us astronomers that study exoplanets, and that is finding another planet like our own. We want to answer that question: is Earth a unique place in the universe, or a common outcome of planet formation, or something in between? And so in order to do that, we have to move towards the small stars to study the small planets, like Julien has said. And so for a long time, there was a hunt for finding a nearby small planet around a small star that we could study in detail. And what was so amazing about TRAPPIST-1 in 2016 and 2017 is at one of the closest possible ultra-cool dwarf stars, not only did we find one transiting Earth-sized planet, but we found 7 transiting Earth-sized planets. Everything from planets hotter than Earth, getting scorched up on a 1.5-day orbit around this star, to planets what we think have temperatures comparable to what we experience here on Earth, to planets that are cooler. So this system has received more interest than really any other exoplanet system, because it has just got this amazing just this whole circus of planets that are Earth-sized that we can study today with our current technology.
Julien?
Well, Ben has already said a lot, but maybe one thing I'll add to that is the fact that it's really worth appreciating how tightly packed they are with their star. You know, like if you think of the distance between the Sun and Mercury, the closest planet to our star in the solar system, the furthest in the TRAPPIST-1 system is still, I think, 20 times closer to its star than Mercury is to our Sun. So it's really tightly packed, and yet the system appears to be very old. And the beauty of this system, which is also important to help us understand the system itself, is that each of the planets are found in resonance chain, meaning the ratio of one orbital period to another is a ratio of integer. So it's basically a Swiss clock for astronomy. And that type of very specific configuration helps us understand tidal interaction, but also provide us with constraint on the mass of the planet that we would not be able to get any other way. And knowing the size and the mass of the planet help us understand what they are made of, the bulk composition. So this system is great in various ways, including what you just described.
I think it's wonderful that the universe provided us 7 planets like the 7 dwarfs. So we're going to concentrate on B and C because there's a paper about them. And what I've learned from the paper is that they have possibilities. You bracketed them. They're either without an atmosphere and solid rock, like Mercury, Julian, you instructed me, or they're Venus. Benjamin, what does that mean? Are they Venus? How did you perceive that?
So back when we only had the Hubble Space Telescope to look at these planets, we had a limited wavelength range in which we could look for features, but it covers a absorption feature from water. And so there are two possibilities. Either we would see an absorption feature from water, and that would tell us that actually this atmosphere was very extended because the precision of HST was great, but it's not as good as you need to study a compact atmosphere like Earth has. Or we could see nothing, and that would say that either the atmosphere is not there or that it's shrouded. Their absorption features are covered from hazes or clouds in the atmosphere. And so with HST, with the Hubble Space Telescope, the conclusion was that we don't see a clear spectroscopic feature. And so we're either looking at an absence of an atmosphere or an atmosphere that's cloudy. Now the picture has changed a bit with JWST because we have new wavelengths to look at, and we have better precision. And so some recent studies have looked at the thermal emission from the planet as it passes behind the star, and that tells us how hot the day side of the planet is. If the planet has an atmosphere, some of that heat that hits it from the star can be advected onto the cooler side of the planet, and you end up with more of a less contrast between the day side and night side brightness of the planet, or the temperature of the planet. But if it does not have an atmosphere, that heat that hits the day side of the planet will stay there. You'll have an extremely hot, scorching day side and a cold, dark, frozen night side. And then you end up seeing more thermal emission with the JWST measurements. And that's what people think they've seen so far with the preliminary results from JWST. So the current picture is that the innermost planets in the TRAPPIST-1 system, B and C, don't have atmospheres. They're just bare rocks with scorching day sides and cold night sides.
Do each of you have a favorite of the 7 planets that you like to study, and why?
Julian?
Wow, that's a really good question. Can I escape it by saying that we really need each of them to help understand the other, or you want me to go down with one? Because if you want me to go down with one, I'm probably going to be placing a safe bet and going for F.
Why?
I was hoping to avoid that follow-up question.
Well, there's sleepy, there's dopey, there's dark. Yeah.
Good point. F. I'm trying to stay within the habitable zone while moving as far as possible from the star, basically, because right now it seems like B and C, which are outside of the habitable zone, close to the star, may have lost their atmosphere over time, being eroded by the effect of stellar activity. And so the further away you go, the colder the planet, the easier it is for a planet to be shielded from the effect of stellar activity, and the easier it is for the planet to hold on to its atmosphere. And so that's probably why F and G might be interesting in that context. But all of them are, and as we'll talk about in a bit, B and C, which may not have an atmosphere, are key because we get to study their atmosphere, their surface property if they don't have such atmosphere. And also, and most importantly, we can use them to play a trick when we do data analysis to actually correct for the effect of stellar contamination and then enable the study of the other planets. So it's really a family, and each member has a role to play in our exploration.
Oh, you're a good parent, Julian. No favorites. Benjamin, who's your favorite, but you'll admit to?
Well, I would go with F as well. I think Julian and I are thinking a lot along the same lines. And, just to add a bit, I wanted to just explain why all 7 of them are important. And that really boils down to the fact that astronomers like us don't get to make experiments. Chemists, other types of scientists can go into a lab and they can control everything precisely and measure things out and change one variable and see what the impact is. But astronomers are just stuck with what we can find in the sky. And so, a lot of the issues that come up when we're trying to study the great diversity of exoplanets that are out there is like, why is this that way? Why is this planet so close to its star? Why does this planet seem to be inflated? Why does this planet seem to be hotter than we would expect? And often there's too many confounding variables to sort it out. But in the TRAPPIST-1 system, we have 7 planets that are almost exactly the same size, that have had the same history orbiting the same star for billions of years. And so we can do this comparative exoplanetology that we've always dreamt about. We can think of experiments of what would happen if you took an Earth-sized planet and moved it closer to the sun than Earth is, or what would happen if you took an Earth-sized planet and moved it further away from the sun. And in the TRAPPIST-1 system, if we just study all 7 of them together, we can start to answer those kind of questions.
The atmospheres themselves, if they have an atmosphere, and B and C do not, so they're control. If they have an atmosphere, what are we looking for in the atmosphere? What needs to be there for us to say, Eureka? What are we expecting? Julien?
Thank you for asking that question. What are we expecting is a good question. I would say we are expecting first and foremost an atmosphere not too far away, if there is an atmosphere, from what we see on Venus. Like the dominant perspective on what type of atmosphere can terrestrial planet form is something like Venus. So dominated by carbon dioxide. It's also what we find on Mars. And by the way, it's also what Earth would have if we didn't have ocean and water cycle to wash that out of the atmosphere. So if those planets are not harboring liquid water or any other volatile that can help remove the carbon dioxide from the atmosphere, that would primarily have carbon dioxide. 2 other options, primarily, right? There would be many other compounds. 2 other options would be nitrogen, just like Earth. If carbon dioxide is removed, nitrogen tends to be the second dominant species, so it would be the first one if CO2 is removed. Or dominated by oxygen is another option amongst many, but these are the 3 that we could talk about.
David, you have a question?
Given those descriptions, I guess it would be really rare to find human or some kind of life biosignal based on life as we know it. So could there be life as we don't know it that you could discover in the TRAPPIST system?
Benjamin?
Yeah, there's been a whole slew of research in our community looking at potential biosignatures, starting from life as we know it. If Earth were out there in the galaxy, what would we look for to identify it? To what other kind of ideas can we think of that might point towards life? There's a good argument that life, no matter how we find it, would have some sort of basis with carbon. Carbon is a very interesting atom, can form really complicated, unique molecules that we give a whole classification, organic molecules, because all of the strange and interesting things carbon can do. But it's possible that the biology doesn't exactly work the same way as ours, and so maybe ozone or oxygen isn't as such a good biosignature as it is on Earth. But in general, what people would look for is some sort of disequilibrium, some combination of molecules that are present that we don't think should be present if we allowed them to interact without any sort of thing producing more of them, or some molecule that's missing that we would expect to be there.
Julien, how did the 7 dwarfs get stacked up so Cinderella can go bang, bang, bang on their heads? How did Snow White? Why are they there so close in? I understand from one of the papers they've migrated. What does that mean?
Again, fantastic question. So one of the preferred path forward with this is that when a star is born, it's actually born within what we call a molecular cloud that collapses, and at the center, the star forms, fusion can start, and on its outskirt, we have a planetary disk. Right? And as the star starts burning its fuel, starts shining, it progressively clears out the disk in its vicinity and then further and further and further away. So what we think is that within that disk, planet formed, and they were interacting gravitationally, so they were tugging at each other as they were rotating around the star. But as the disk cleared, the disk allowed for enough friction for the planet to lock into resonances. And so that resonances, which is difficult to get to, was enabled by the presence of the disk. And each of the planet locked with the previous one progressively as the disk was fading away. And as they locked and the disk fade away, they managed to drift closer to the star. And by the time the disk was cleared out, they were just close to their star and nicely set in a resonance that can last for billions and billions of years. Right? We believe that the TRAPPIST-1 system is twice as old as our sun, which is really important because it also means that if any of these planetary systems are habitable or inhabited, they could outlive any planetary system and civilization around sun-like star, which don't live for as long.
They move towards the sun. Are they still moving, or
they're stabilized now? They stabilize each other.
And that's a good thing. And Benjamin, a question, because I skipped it. What does it mean, habitable zone? What are you looking for?
So if you're too close to your star, it's too hot for water to form on the surface of a planet. Any water that's there will be evaporated and eventually lost through the upper atmosphere. And if you're too far away from your star, you do the same experiment by taking Earth and moving it in and moving it out. If you took Earth and moved it out in our solar system, eventually all of the water would freeze. We wouldn't be able to have plate tectonics or sort of any exchange with the atmosphere, and then it would be a hard sell for life. Not saying it's impossible. There are water-rich worlds in our outer solar system, the moons of the gas giants, that might have liquid oceans that are conducive to life. But for Earth-like life, where we have all this abundant life on the surface, it would be a hard sell. So the boundaries between where you could expect liquid water to be on the surface of a planet is what we call, in short, the habitable zone.
Habitable zone. And some of these 7 are in the habitable zone. David, you have a quick question.
Are you expecting to find another TRAPPIST-1 system where our technology will allow us to study? And if not, what other kind of system would you want to find that would be exciting to study given the constraints of our technology today?
Julien?
Yeah, it's great questions. Wow. It's really a pleasure to talk with you guys. So to answer your question about other TRAPPIST-1-like system, TRAPPIST-1 was found with a prototype telescope called TRAPPIST in honor to the Belgian monk that produced the TRAPPIST beer. And we only searched for planetary systems around 50 ultra-cool dwarf stars before we made that discovery. And after that was a success, we moved on to another project, the parent project to TRAPPIST, which is called Speculoos, in honor this time to Belgian cookies, Speculoos cookies. And their goal is to search for planetary systems like TRAPPIST-1 around 1,000 ultra-cool dwarf stars. So we do expect a handful more systems to come through that. They may not be as good as TRAPPIST-1, but they'll be great for the James Webb Space Telescope for sure. And they might be slightly better, by the way. So that's an answer to the first part of your question. For the other part of the question, another configuration where we might be able to access Earth-sized planets will be again around very small stars, but this time on the other side of the lifespan, which is the white dwarf, right? White dwarf also extremely tiny. And so if you were to find Earth-sized planet around white dwarf, they could be the remnant of a planetary system after the death of the main star, and the core turning into the white dwarf would be small enough and bright enough to still allow us to do everything we're talking about. So that would be another exciting configuration. And to the best of my knowledge, we've not found Earth-sized planet around white dwarf yet.
We're going to turn to a wish list. We're going to give each of these distinguished gentlemen an unlimited budget. What is it they want to achieve, either in TRAPPIST-1 or in the search for something unusual? An unlimited budget. You write it, you hire it, you go for it. Where do you want to go?
Can I give you 2 ideas?
Of course.
Okay. So within sort of the realm of possibility, but assuming we had unlimited budget, let's say we turn the James Webb Space Telescope into the TRAPPIST-1 Space Telescope, and we basically dedicate our premier facility in space to observations of the transiting planets in this system, it's possible that given a large enough data set, we can overcome this issue that we've discussed with stellar contamination or the transit light source effect, and understand exactly what are the signals that are coming from the star when we get transit observation and what are the signals that are coming from the planet. And then we can do these atmospheric studies of all 7 planets to really answer that question of what would happen with an Earth-like world, hotter than ours or cooler than ours or just like ours. Could we find an interesting signature in its atmosphere that would point towards life? That's going to require unlimited budget, but it's in principle a feasible thing we can do with the current technology. The other idea I want to pitch is something called the Solar Gravitational Lens Telescope. This is an idea that's floated around ever since Einstein pointed out that gravity bends light. It can bend space-time and it can bend the path of light. And I think shortly after that, people pointed out, well, if you had a receiver out about 550 AU from our star, 550 times the distance of Earth to the sun, you could use the sun as a telescope, and you could magnify images behind the sun by bending all of the light to focus at that point. You would just have to have a star shade in front of you to block out the actual light coming from our sun. So if we manage to pull something like this off in the future, the solar gravitational lens, I did some calculations, and the resolution of a telescope that had light magnified by our sun would be 10 to the minus 7 arc seconds on the sky, which is many, many orders of magnitude more refined than what we can see with any of our current telescopes. That wouldn't just allow us to resolve the TRAPPIST-1 E, for example, from the star TRAPPIST-1. It would allow us to actually resolve surface features on TRAPPIST-1e. We wouldn't have to worry about the transit light source effect anymore because we don't need to worry about the transits. We can study the planet as itself, and we could actually resolve continents or oceans if they existed on this planet.
How big, how far out? AU, how many did you say? 500?
550 AU.
Okay, done. Julie?
Well, funny enough that we have not talked about this, but that's exactly where I was going with this. And it has a name. It's called a Van Neumann probe. And so you can, I put a wiki link in the chat there. You can check it out. So there'll be a 2-step plan, actually a 3-step plan. What we can already do with current technology is appreciate the fact that if other species have understood what Ben just described, which is quite likely if they are more advanced than us, then there might be Van Neumann probe in our own solar system. And we have the technology to look for that out at 550 AU. So we could look for such probe to search for signs of intelligent life in our own solar system. That's step 0. Step 1 would be what Ben described, where we developed our own probe to be able to study other planetary systems from our own planetary system. And then step 3, which I think is really the exciting one, especially when we consider where we're going with AI and quick advancement with robotic, is to send our own fleets of probe out towards other planetary systems. Because at the end of the day, we need to be able to go there to get a sense of what is happening. Like, there's only so much we can do remotely. And if I were to tell you tomorrow we found signs of life elsewhere and I show you data that really comes back from one bright data point on my detector, would you believe it? Well, to some extent. If we send probe all the way out there and you get to have a full detail of what's going on in that planetary system, you probably buy that more easily. And so I really think that if we move towards step 3, where we just send a fleet of probes, that's really what is exciting in the context of an infinite budget.
David, we have a couple of minutes if you have a question about their wish list.
Julian, when you say send our own probes out there, are you thinking along the lines of something like Breakthrough, where we reach maybe a quarter the speed of light and it takes longer than our lifetimes to get maybe 1,000 microchip wafers that fly by really fast because they can't slow down? What kind of information could you get back from something that tiny over that many light years?
We have about a minute, Julian.
I completely agree with you. I think there's a fundamental limitation with reaching that speed. And then we may ask ourselves the question, what is the benefit of traveling at that speed when considering how would we decelerate? Because at the end of the day, if you want our own Van Neumann probe out there, they need to be in a stable orbit, right? They don't have to Zwift through. So I think the speed isn't necessary if we give our species the time to get to the system and have probes that are established and can do for whatever time we need the science that needs to be done there.
Gentlemen, I like the way you spend money. When I said unlimited, you took it. Wow. Okay. Julien de Wit, Benjamin Rackham, MIT, TRAPPIST-1 is the star. The 7 dwarves are being studied and to be studied. David Livingston, Dr. Space of the Space Show. This is Hotel Mars, Episode N. I'm John Batchelor.